Welcome to the today's session. Good afternoon, everyone. This is the second section on composite sections. In the previous class, we have discussed about the introduction about the composite section and also the different types of sections in composite section, and also we have learned about the analysis of composite sections. In the present session, we will try to discuss about the design of composite sections, okay, and also the design of horizontal shape reinforcement. Now here, in the design of composite sections, normally what we'll do, we'll design. The design is based on satisfying allowable stresses. We need to satisfy what are allowable stresses under service load and transverse load. Means we need to calculate stresses at service condition and also at transfer condition. Then we need to check whether these stresses are within the allowable stresses or not. Okay, that we need to check, and along with that the section should be analyzed for the ultimate loads. Okay, we need to analyze the section for ultimate load to satisfy what is limit state of the collapse. Okay, the same procedure what we have seen in your model number 4. Okay, same thing we are using here. Okay, there also we have done the design of conventional PSA beam. Okay, the procedure is almost same. The member is also checked to satisfy the criteria of limit state of serviceability. Means after designing, after checking the allowable compressive stress and also for analyzing for ultimate load, okay, then we need to check whether that member is serviceable or not. We need to check for the limit state of the serviceability. Okay, what is the limit state of serviceability? We need to look about the deflection and also the crack width in case of type 3 members. Okay, means these things we need to take care whenever we are designing what your composite beam. Then here what we are doing, before the calculation of initial pre-stressing force P naught and eccentricity, because whenever the design of the PAC beam comes, first we need to calculate how much pre-stressing force we need to apply, what is the initial pre-stressing force, and also what is the eccentricity of the steel cable. Okay, that we need to calculate. But here, before the calculation of these two values, okay, at the critical section, okay, then what we are doing, we need to decide the type of the section and also the stages of pre-stressing, because we have seen in the previous session the type of composite section. There are the different types of the composite section. Okay, first we need to decide which type of composite section we are doing and what is the stages of pre-stressing we are doing. Okay, that we need to decide before calculating your P naught and also the eccentricity E of your steel cable. Okay, then subsequently we will do what a trial and error procedure is adopted for what a design. Okay, in this way we can adopt a trial and error procedure, okay, for the design of your composite sections. The following steps explain the design of composite section with precast web and cast in place flange. Okay, it is for what if when the precast web, here the web is precasted and flange is what if cast in place. But the precast web is pre-stressed before the casting of flange. Okay, the precast web it is pre-stressed before the casting of flange. Okay, then this is the member we have taken is what a type 1 member. Okay, we know there are three types of member: type 1, type 2, type 3. Okay, we are discussing about in detail in the model number 3 and model number 4. Now in the step 1, we need to calculate the eccentricity. Okay, to calculate eccentricity, first I need to with a trial section of web. Okay, I need to assume a trial section of the web. Then the CGS located at the maximum eccentricity. The CGS located at the maximum eccentricity Emax. Okay, this can be calculated. Okay, means here with the trial section of the web we can calculate the maximum eccentricity. Okay, that maximum eccentricity we can calculate based on the zero stress at the top of the precast. Okay, we need to calculate the maximum value of P so that at the top, the stresses at the top, it should be what here? 0. Okay, and this will use what here? Economical solution, because we know that always we need to make what here? The tensile stress is equal to 0. Okay, that's why the stress at the top, it should be what here? 0. Then the following stress profile will help to determine what is the E maximum value. We will see that stress profile here. So this stress profile we have seen in your model number 4 also. Okay, this is the your web section. Okay, it is CT and CB. CT and CB means the distance between from your CGC to the extreme fiber. Okay, for top fiber and also what is bottom fiber. And E is the eccentricity of cable, and FB is the stress at the bottom, and the top we have taken as what? 0. Now here we have seen from your model number 1, model number 2, okay, how to calculate the KT and KB. Okay, the current point, the bottom current point and top current point. Okay, these are the points, okay, in which the compression force is active. Okay, it is the maximum distance at which compression force is active. Now to calculate this, now here I need to calculate this E value. If you want to calculate this E value, okay, but so that at the top your stress should be what is 0. Okay, to calculate this, okay, by here we are have the expression Emax is equal to Kp plus MSW divided by P naught. Okay, this expression we have derived in model number 2. Okay, that's why I have taken expression directly. Okay, where Emax is the maximum eccentricity of your the pre-stressing cable. Kb means it is a distance of bottom current point of precast web from CGC. See, all this we are doing with respect to precast web only. We are not taken steel water, the flange. Then MSW is the moment due to the self weight of the web, and also P naught is it is a trial pre-stressing force at transfer, because just we have assumed this value. Okay, we need to assume this P naught value because we don't know this value. Okay, just we are assuming this value. In this way, in the first step, you can calculate what is the maximum eccentricity. The second step, we need to calculate the equivalent moment for precast web. Okay, what is this equivalent moment for precast web? See here, a moment acting on the composite section. Okay, the moment which is acting on the composite section, because we know that the section will not behave as a composite section immediately. Okay, but a moment acting on composite section is transferred to an equivalent moment for precast web. Means the whatever the moment which is acting in composite section, it is transferred to an equivalent moment for precast web. Okay, so that we can consider only the precast web while the designing your beam or while analyzing your the beam. And this is done to compute stresses in the precast web in terms of properties of precast web itself. Okay, here this we have done because to calculate what is only to calculate stress in precast web, so that it is in terms of what is the properties of precast web itself and not the composite section. Because of this reason, we are transferring the moment on the composite section is transferred to what is equivalent moment for the precast web. Okay, now for a moment MC which acts after section behaves like a composite section. For example, if FC is the moment, okay, which acts after the section becomes what a composite section. We know that when it will become composite section, because initially we have only the the web is precasted. Okay, that is pre-stressed. Then afterwards we will do the casting of flange, and once the flange has attained the complete strength, then afterwards it is behaves as what a composite section. Now at that point, if moment is MC, okay, and moment is MC, if it is acting, then section will behave as what a composite section. The stresses in extreme fibers of precast web are determined from the following stress profile. Okay, if this is the case, then how we can calculate the stresses in your precast web? Now here you can use this expression. Okay, see, this is your the web and this is what your flange. Okay, now this is from CGC up to the top fiber, it is CT double dash, and here it is up to the your the intersection between your top flange and web. This is what is CT dash, and this is CB dash. Okay, this is what is breadth of your web, and here I need to calculate the stress at this the intersection of the web and flange and also at the bottom point. To calculate this, Okay, we have ft is equal to the mc into ct dash divided by I dash. Okay, ct dash, it is due to what here? It is up to the intersection of your what, the junction of your web and the flange, and mc into cb dash by the I dash. Okay, in this way you can calculate what is your stress at top and bottom. Okay, in the web portion by transferring the stresses, by transferring the moment in composite section into what is the equivalent moment in the precast web. Then these are the expressions, same thing. CGC, centered of the composite section. CT dash, the distance of top of the precast web from CG dash. Okay, then CT double dash, distance of top of the composite section from CGC dash. Okay, this will indicate with respect to what is composite section. And CB dash, distance of bottom of the precast web of the composite section, and from CGC I dash is what a moment of inertia of the composite section. Okay, these all dash are related to what are related to what is the composite section. Then the following quantities are defined as the ratios of properties of precast web to the composite section. Okay, to convert to equivalent moment, okay, these all things we are doing. Okay, here we have taken the ratio of what is properties of precast web to the composite section. Here the empirical factor mt is equal to what is I by ct. Okay, I by ct divided by I dash by ct dash. This I by ct is due to what is due to the normal section, and whereas this I by ct dash, it is due to what is it is due to the composite section. And similarly mb is what I by cb divided by I dash by cb, means the properties of precast web to the what is the composite section. In this way you can calculate an mt and mb, and so that the stresses in extreme fibers of precast web can be expressed in terms of mt and mb. Okay, therefore the top stress at the top fiber is equal to mt mc ct by I, and where if you convert the ct into I, mt into mc divided by akb. Similarly, the stress at the bottom is equal to mb mc a kT. Okay, mb is this, mc is the moment at when the composite section is acting. Okay, a is the area of the your section, and kT is the water, the top curve point. This now we have seen the quantities MT, MC, MB, MC are the equivalent moments. Okay, I already told this we are doing only to convert what is equivalent moments. Thus, the stresses in precast web due to MC are expressed in terms of what is precast web itself. Because of this reason only, we have converted everything into what is equivalent moments. And after this, you can compute what is P, effective pre-stressing force. Let MP be the moment acting on the precast web prior to the section behaving like a composite section. Okay, then after MC is applied on composite section, the total moment of precast web is MP plus MB into MC. Okay, this is what this is the equivalent moment. Okay, initially the before it is there like a the composite section, it is what it is mp, but after the mc is applied, okay, that is what is mb into mc, what the equivalent moment in the web. Okay, therefore the total moment is equal to mp plus mb into mc, and therefore for type 1 member the stresses due to service load is equal to what is 0. Therefore what we can write, pe by a. Okay, this is due to the your the pre-stressing, your pre-stressing effective pre-stressing force, and this is due to the due to the eccentricity pre-stressing force due to the eccentric pre-stressing force, and this is due to what here, this is due to the total moment. Okay, the total moment before your web page act like composite section, and after the mc is applied on the composite section. Okay, in this way if this is equal to 0, okay, this way is equal to what, 0. Therefore your pre-stressing is equal to what, this is the equation. By using this expression you can calculate what, effective pre-stressing force. And note that the pre-stressing force is acting only on the precast web, and C is the eccentricity of the CGS from the CGC of the precast web. Okay, this you need to keep it in mind. Then the step number 4, estimate P naught, the initial pre-stress instance as follows. The A is 90% of initial pre-stress, initially applied pre-stress for pre-tension member, but if it is post-tension member, it is equal to what? A PA. Okay, then the value of PA is equal to what? AP into 0.8 FPK. Okay, then after calculating this PA, okay, here AP is equal to what? We know this expression where AP is equal to PE divided by 0.8 of FPK. In we know PE value, we know FPK value, you will get AP. If you get AP, then you can calculate what is PA. If you know PA, you can calculate what is this, the pre-stressing force. Okay, this P naught. Okay, hence, then based on this new P naught value, once again you can calculate what is Emax. Okay, initially you have calculated Emax with assumed value. Now you can calculate Emax once again with the new updated value. Okay, once again you substitute that value. Once again you will get what is the Emax. Okay, as with the new value of P naught. This you need to then check for the compressive stress in the precast web. Okay, then after doing, calculate the stress at transfer. Okay, at the bottom. Okay, it is, this is due to the pre-stressing force, this is due to the eccentricity, and this is due to what? The self weight. Okay, you will calculate what? FP, and the stresses, this should be, it should be limited to what? FCC allowable. Okay, it should be less than what? FCC allowable. Okay, compressive stress, allowable compressive stress in the concrete. Okay, this you can see as per figure number 8, IS 1343/1980. Similarly, calculate the stress at the top at service and check once again whether these values are less than the allowable compressive stress in concrete as per figure number 7, IS 1343/1980. Okay, if it is not satisfied, then just you increase what your A value, and once again you revise the procedure, repeat the procedure. The step number 6, calculate the compressive stress in the flange. Okay, that is equal to what? Ft dash is equal to mc into ct double dash divided by I dash. Okay, then check once again this value also whether it is less than fc allowable or not. Okay, in this way we have to design your composite section. Okay, this is the brief the procedure to design what? The composite section. Now we'll go to the last topic. Okay, that is what? The analysis for the horizontal shear transfer. Okay, means we need to calculate shear strength and we need to provide what? The shear reinforcement. Okay, here with increase in the load, the bottom face of the CIP portion, means cast in place portion, means your flange portion, okay, tends to slip horizontally and move upward with respect to the top face of precast portion. This here, if this is your the web portion, okay, and here you will have what? Here you will have the flange portion, and whenever it is subjected to any load, okay, normally what happens, the in between your flange and the web, at this point, okay, you will getting what? Slip. Okay, this may slip, the flange may the slip like this. Okay, it may slip from here, or sometimes, okay, it may go away here like this. Okay, it can move up like this. Okay, to prevent this, okay, this will happen. If you want to reduce this, then here what we need to do, here we need to provide some reinforcement at this point, vertical reinforcement, and this reinforcement, okay, it is called as what? A shear friction reinforcement. Okay, due to here what is happening, the slip is happening, and also it is jumping from the two things, flange and web are separating. To prevent this, to develop the composite action, because this will reduce whenever it has developed what? A composite action. To develop the composite action, we are providing a vertical reinforcement, that is called as what? A sometimes shear connectors. Okay, that is what? A shear friction reinforcement is provided. Then how to calculate this reinforcement? The required shear friction reinforcement per meter span is calculated by using this expression, 1000 BV by tau h 0.87 Fi mu. By using this expression, you can calculate what is the shear friction reinforcement. Then here, the minimum requirements of shear friction reinforcement and spacing are similar to that of shear reinforcement in the web. Okay, the spacing and minimum shear reinforcement, everything it is same as your normal shear reinforcement in the web. In the previous equation, ASV is equal to area of the shear friction reinforcement in mm square per meter. BV is the width of the interface of the precast and CIP portion, and horizontal shear stress at interface, and Fi is the yield stress in Newton per mm square. Mu is the coefficient of friction. It is 1 for intentionally rough interface with normal weight concrete. Okay, in this way you can calculate what is the shear strength of the your shear friction reinforcement. Okay, due to what is the horizontal shear transfer. Okay, then in the shear reinforcement in web can be extended. See, whatever the reinforcement we are providing in the web, okay, the same reinforcement we can extend what here in the in your CAP portion. Okay, this flange is called what is cast in place portion. Okay, then it is anchored in CAP portion to act as what is shear friction reinforcement. Okay, in this way you can provide what is the shear friction reinforcement. Now we will see the one example on this. Okay, then we'll end up the session. Then the example is the midspan section of a composite sectional beam. A midspan section of a composite beam is shown in the figure. Okay, the figure is there in the next slide. The precast web 300 by 920 mm depth is post tensioned with initial initial force of P naught 2450 kilonewton. Effective pre-stress is estimated as 2150 kilonewton. Moment due to the sulfate of the precast web, MSW is what? 270 kilonewton meter at midspan. After the web is erected in a place, okay, then after erection of the web, the top slab 150 by 290, 150 by 920 mm width is casted, producing a moment of CIP 135 kilonewton meter. Means the top slab is flange, okay, 150 mm by 920 mm width is casted. Okay, it is what is unpropped. Okay, you have seen what is unpropped and what is propped. Okay, producing a moment of water. The moment due to the cast in portion is how much? 135 kilonewton meter. After the slab concrete hardened, the composite section is to carry a maximum live load of 720 kilonewton meter. Okay, this is the data what he has given, and you need to calculate stresses in the section at various stages. Okay, we will calculate all the stresses in the various stages. This is the section what he has given. The depth, this is how much? This is 920. The depth of the slab or flange is 150 mm. The effective width of the flange is 920 mm. This is what? 300 mm. And this it is what? It is 200. Okay, your cable is there at a distance of 200 from the bottom of your beam. Then initially we need to calculate geometric properties for precast web. Okay, only for the web you calculate the area. Okay, and calculate the I value. Okay, area is equal to your BW into the depth. Okay, BW is I think 300, depth is I think 920, it is there. You multiply that, you will get this area. I means BD cube by 12. Okay, means 300 into 920 cube by 12, you will get this answer. Okay, then the distance of CGC, as the web is a rectangular section, the total depth is the 920. Okay, better you can see here. Okay, this depth is 920. Then your CGC only for this web, the CGC will be at the center. Okay, this you can take it as 920 divided by 2. Okay, 920 divided by 2, it is how much? 460 mm. See, these geometrical properties are only for the precast web. Okay, we are not considered what is the flange or cast in place portion. And similarly for composite section, means for composite means for entire, both for your flange and web. Okay, for total section, calculate area. Because here the area is increased because this is area only due to the web portion, but this is the area due to what both the web and also what is the flange portion, and this is I due to both your web and flange portion. Okay, in this way you need to calculate what is the A value, I value, and the distance of CGC from the bottom. Okay, before we have taken only web, but here it is what is entire T section. Use your so-called your formula what you learned in your engineering mechanics. Okay, A1 into X1 plus A2 into X2. Okay, all divided by what is A1 plus A2. If you use that, you will get what is this the distance. Okay, these things we have done. in the previous models. Okay, that's why I have reduced all those calculations directly. I've taken the values. Okay, because I think that you can able to calculate all these the section properties. Okay, the geometrical properties. And this is what we got. Okay, this is a CGC due to the web portion, but CG dash it is due to what? It is due to the composite action. Okay, and this is at 460 from the bottom, whereas this is at 638 from the bottom. Now the calculation of stresses in the web but transfer. Okay, already we have derived this formula. The stresses in the web but transfer is equal to what? P naught by A plus or minus P naught into EC by E into C by I. Okay, this is due P naught he has given as 2450 in terms of kilonewton he has given. I am converting into Newton. Area we have calculated. P naught we know. Eccentricity he has given as 260. Okay, because from the bottom it is from here to here it is 200. If this is 200 and this will be is equal to what? 460 minus 200, it will be 260. Okay, this is 260 and this 460 means is what? It is C, means the distance from CGC to the extreme fiber. Okay, up to here to the here. This is what is the 460 and here this is I value for the web portion. And similarly the moment to the sulfate is given, but I am converting into Newton mm. Okay, 10 raised to 6. C is 460, I is this one. If you substitute all these values, if you take the positive, you will get what a top stress. The ft is equal to minus 0.22 Newton per mm square. But if you take this the bottom minus, you will get this as what, minus 17.54 Newton per mm square. This is at the top and this is at the very bottom. Okay, stress at the top, stress at the bottom in the web at transfer. At a transfer means you have only the self weight of your web. Okay, still the flange is not constructed. Okay, now stresses in web after long term loss. Okay, after it has attaining the complete strength by that web. Okay, then it is subjected to what, a long term loss. Whenever it is subjected to a long term loss, you will get what, a instead of the P naught initial pre-stressing force will get what, a effective pre-stressing force. Okay, this is the effective pre-stressing force. It is a force due to what, a after the all losses. Okay, then again PE by A, this is due to the eccentricity, this is due to what, a sulfate. Okay, then here if we know all the values, only thing is what, a P also is given. If you substitute all the values, you will get stress at the top as minus 0.97 Newton per mm square, stress at the bottom as minus 14.61 Newton per mm square. Okay, these are the stress at top and bottom in the web after what, a long term losses. Then the calculation of stress in web after the casting flange. Okay, now it is after the casting the flange. Okay, after the casting the flange, stresses you will get the stress due to P, and it is stress due to the eccentricity of the P, and this is due to what, a self weight of web, and also what, a self weight due to what, a your casting portion means your flange. Okay, then if you use this formula, you know P, P, E, C, MSW, MCAP also has given the given value. If you substitute all these values, okay, then here it is what, the stress at the top is equal to minus 4.16 Newton per mm square. Stress at the bottom is equal to minus 11.42 Newton per mm square. Okay, in this way you can calculate stresses at the top and bottom whenever the in the web after the casting of the flange or the cast in portion. Then we need to calculate the stresses in composite section at service. Okay, now it is behaving as a composite section. We need to calculate stresses at service. Okay, and here we need to consider what is stress due to the live load moment. Okay, stress due to the live load moment is equal to what? That the top fiber, the formula already we have seen, expression already we have seen, MLL into CT double dash divided by I dash. MLL is given CT double dash. Okay, we have calculated in the figure. We substitute that 432. Okay, this I dash also we know because these are the properties related to what, is properties related to the composite section. Okay, then you will get the stress at the top is equal to minus 7.01 Newton per meter square. Similarly, the stress at the bottom is equal to MLL into CB dash by I dash. Substitute the values, you will get this as what, 10.36 Newton per mm square. Okay, these are the stresses at top and bottom due to what is the live load moment. But at a top fiber of precast web, okay, at the top fiber of precast web, the stress due to MLL is calculated from proportionality of triangles. Okay, proportionality of triangles, and that it is calculated as Ft is equal to minus 7.01. Okay, multiplied by 282, 32. If you make the interpolation, you will get this as what? Minus 4.57 Newton per mm square. It is the stress due to the live load moment. Okay, at variance at the top fiber of precast web. Then the total stress in the precast weld. Okay, at the top fiber, already you have calculated this minus 4.6 minus 4.57. Okay, here you can see this is 4.57. Okay, it is stress at the top of the precast web due to water live load moment, and this is the total stress at the top what we calculated minus 4.16. Okay, here it is 4 minus 4.16 minus 4.57. This is almost minus 8.73 Newton per mm square. Similarly, for bottom fiber, minus 11.42 plus 10.36. Okay, this is almost minus 1.06 Newton per mm square. And therefore, the total stress in CAP slab. Okay, the total stress is due to what is MLL only, because the CAP is subjected to only what is live load moment. Okay, therefore, already we have derived. Okay, the I think here you can see here it is the stress at the top, which is not okay. It is top means what if for precast it is top, but for cast in place it is what is bottom. It is almost minus 4.57 Newton per mm square. Okay, I think better you need to make this correction. This is not at the top. Okay, sorry, it's not the top. Okay, this is at the this is at the bottom. Okay, this is at the bottom. That is how much. Okay, I think here it is correct is there. Fp dash minus 4.57 Newton per mm square. But this is at the top fiber. Ft dash is equal to what? Minus 7.01 Newton per mm square. Okay, this also you can see here. Okay, this is at the top fiber. Okay, this is what? Minus 7.01 Newton per mm square. In this way, you can calculate the stresses in all the fibers. Okay, in the all the stages in your the web. Okay, of the composite section. And by after computing all the stresses at the transfer, the stress at the bottom is this, stress at the top is this. After the losses due to the PE value, this is due to the P naught, this is due to the effective pre-stress, this is the top and this is the bottom. And after casting your CAP portion, flange portion, okay, here it is top, it is minus 4.16, bottom it is minus 9.42. And this is due to what? The live load moment at the top and in between junction at bottom. Okay, therefore the total stress is equal to, okay, the total stress is equal to, okay, the total stress, the total stress is equal to this plus this. Okay, this the two will give, okay, these three things. Okay, this will give what? The total stress. Okay, this is the total stress what we got at the service. In this way, we need to calculate the stresses in your the composite section at all the stages. Okay, with this I will try to end the today's session. Thank you for watching. If you have any doubts, please contact in your WhatsApp group or in the YouTube link. I will try to answer those questions. Okay, have a nice day. Thank you.